Part sequence looking at supercells and tornadogenesis. Part 1, we considered supercell formation, the development of the mesocyclone. Part 2, we looked at non-mesocyclone tornadogenesis, which is a simplified version of what we're going to look at here, which is tornado formation with mesocyclones. Okay, our learning objectives would be to describe the physical features related to mesocyclonic tornadogenesis, and then, of course, be able to identify limiting factors, which are equally important because most supercells are not tornadic. So if you can't identify the limiting factors, you're going to run into a false alarm problem very quickly. Okay, here's a case of a classic supercell tornado. This was a long track EF4 from the evening of April 27th, 2014, the Vulcan, Arkansas tornado, which I believe was the deadliest tornado in Arkansas history. There weren't very many tornadoes that day, but when you have one 70-mile track EF4 that hits a town, that, bad things happen. So point here is that you want to be able to identify these storm structures and this sort of potential in the environment as readily as you can without, so that we want to try to share at least some efficient, repeatable ways to identify this sort of storm outcome. And again, these are all characteristic supercell structures, upper left, classic reflectivity hook, even a small potential debris signature with the lofted debris in the tornado circulation. Lower left, a large bounded weak ecoregion indicative of a deep, strong updraft above the storm inflow. Lower right, broad, strong rotation, that's the storm mesocyclone, and that's up at 15 to 20,000 feet. And then in the upper right, you see actually a reflection of the tornado circulation itself, just to the northeast of Vulcan, which is coincident with that high reflectivity little donut signature. So you want to be able to forecast these sort of events, anticipate them in advance, and I'm here to argue that you can do it, and if you do it right, you can do it without high false alarm. Okay, we recall the right-hand rule from the previous lessons where your fingers on your right hand curl in the direction of the shear as you move upward. Your right thumb points in the direction of the vorticity vector, and that's what we think of as the vortex tubes, which is a reflection of horizontal vorticity, which is tilted and stretched in the vertical to provide the rotation source for the mesocyclone. Here we've got SRH, which is storm relative helicity, as a way to quantify those vortex tubes. And then we also talk about baroclinic vorticity. This will be a little more just qualitative in the sense because we rarely have observations on the storm scale of the boundary gradients and sort of thing. But it does appear that vorticity generated in the sense of frontogenesis on the storm scale is related to tornado potential. Okay, mesocyclonic tornadoes. We need a persistent rotating updraft. This is to provide the source for tilting and stretching to maintain the mesocyclone, and also the stretching in the low levels to amplify the vorticity to tornado proportions. And of course, this is a function, as we talked about in lesson 1, of the buoyancy and the environmental vertical shear. And again, we get the pressure perturbation, and this induces a stronger updraft below the level of the maximum pressure perturbation, and this draws air inward and upward in the storm. And that's a big difference with the non-mesocyclone cases. Here we actually have the storm, is, in a simplistic sense, acts like a vacuum cleaner. It's trying to draw air in from below and up, and it can actually overcome convective inhibition in the low levels, and that's what keeps the storm constantly regenerating itself. Now the question here becomes, what's the source for near-surface rotation? In the non-mesocyclone case, we looked at swirlies along boundaries as the primary mode that you would see. Now this is a classic picture. We've got a rotating updraft. You can see the helical, striated nature to the updraft. You notice it's also got a laminar look. That's a clear sign of forced ascent. This is not buoyant at those levels. It's actually the mesocyclone drawing the air in and up and amplifying the spin as you get higher in the storm. The problem here is if you follow the vortex line, when is that vorticity vertically oriented? It's not until you're well above the ground. You can't get vertical vorticity at the ground starting with horizontal vorticity at the ground given only an updraft. So we have to have something else going on to get vertical vorticity at the ground, which is ultimately what we need to get a tornado. The near-surface rotation, again, it's not storm relative helicity directly that's related to that rotation. That just gives you rotation aloft that's related to the mid-level mesocyclone. Now, when we go by detailed observations from some of the Vortex Project field campaigns and lots of other field projects and numerical simulations, it looks like the source for rotation that ultimately leads to tornadogenesis is related to the rear flank downdraft. or what we call here the RFD. Okay, this is a simplistic version of what happens. You see on the upper left, the little inset, we've got the background environmental vorticity feeds the rotating updraft, but for tornadogenesis, you focus on the little green box, and that's what we zoom in on the bigger part of the image. It's the air flowing around generally the north and west side of the low-level mesocyclone is where the vorticity is generated that leads to tornadogenesis. And more importantly, that vorticity has to be reoriented from the horizontal to the vertical. This is where the downdraft comes in. You can't do that with an updraft alone, but if you put a downdraft, you can reorient the vorticity vector. And that's what, this is a simplistic version of that, where you have primarily horizontal vorticity in the face of a downdraft can be reoriented into the vertical. And the little ice skater illustration that if you have sufficient vorticity and stretching, you can amplify that to a tornado. Now, if it's too cold and it's too stable, or the suction from above is too weak, nothing happens. If it's very strong force descent from above and it's not too cold or stable, you can amplify this to a much stronger rotation. Okay, now here's the problem. What do we mean by not too cold and strong suction from above? Well, the biggest problem is you almost never are going to have any observations of this directly. If we somehow had mesonet towers every 100 meters everywhere and vertical profiles everywhere, you might be able to say something. I don't even know that 100 meters would be high enough resolution in the horizontal to really nail this down. So we're going to have to come up with something in the environment that is a proxy for these processes. And we actually have those, and we'll try to look at this. Again, we're going to go back over the whole idea of the supercell, that if you look at this, again, we've got vertical wind shear in the background environment. That produces the horizontal vorticity. And, of course, you need to use a football here in Oklahoma, at least. And this is tilted in the vertical. You've got strong rotation in the mid-levels. Now, the downdraft portion becomes important for getting the vertical vorticity of the ground, as I've already mentioned. We have, in the sense of frontogenesis, if you think of the atmospheric response to frontogenesis, it tries to weaken the gradient. So there's rising motion on the warm side to cool the environment and sinking motion on the warm side to warm it, which is to try to smear the temperature gradient out. But use the right-hand rule, that gives you a vorticity vector in this case. If it's cooler in the storm precipitation area than it is in the inflow, there's a vorticity vector pointing back toward the storm updraft in this case. Now, with the vorticity moving along and with the descent associated with the downdraft, you reorient the vorticity into the vertical. If you get to the low-level mesocyclone where the strong force descent is related to the mid-level pressure perturbation above that, you can amplify it to a tornado. But so the key is, can we get that vorticity reoriented, and is there enough spin and not enough resistance to vertical stretching so that we can actually get a tornado? Okay, the suction from above, again, is related to the mesocyclone strength aloft. The key with some of the environmental ingredients is that the stronger we can get this mesocyclone closer to the ground, the stronger the induced updraft is closer to the ground, the stronger the stretching is closer to the ground. So what do we observe? We tend to see the strengthening of mid-level rotation first. We get surface pressure falls if you happen to have fortuitous observations. Maybe somewhere like Oklahoma or West Texas, you might have a mesonet site. And you'll see noticeable pressure falls. We'll get strengthening near surface inflow in response to that. And then you'll see the laminar cloud features. So you'll have accelerated inflow, strong force descent. And on the storm scale, you're seeing a response, that whole positive feedback related to the pressure perturbation as it strengthens, and especially as it gets closer to the ground.